Welcome back to the Design by Analysis series. In our first video, we introduced the concept of protection against plastic collapse and three ASME approved methods: elastic stress analysis, limit load analysis, and elastic plastic analysis. In this second video, we will move from theory to practice. Using ASME PTB-3 design examples, we will evaluate the top head and shell region of a pressure vessel with each of the three methods. By the end of this lecture, you'll see not only how these methods are applied, but also how the results compare across elastic limit and elastic plastic analysis. Just a point to note, I am referencing the 2025 edition of ASME Section VIII Div 2, so it is possible that the section and clause numbers may be slightly different from older versions. Also, there may be a small difference in the results are due to fact that PTB3 does not provide CAD geometry. We must create our own models based on given dimensions, which can lead to slight variation. First, we will discuss example 5.2.1 elastic stress analysis. Problem statement. Our first problem is PTB3 example 5.2.1. We need to evaluate the pressure vessel using the elastic stress analysis method as per clause 5.2.2 of division 2. The objective is to determine whether the calculated stress, general primary membrane stress, local primary membrane stress, and local membrane plus bending stress are all within the allowable limits specified by the code. The pressure loading inside the vessel is 420 psig. Before starting, let's define the material properties and variables. The head and shell of pressure vessel are made from SA516 material and the top forging is made from SA105. S is the allowable stress from section 2D, Sy is the yield strength, St is the tensile strength, E is the modulus of elasticity from section 2D from table TM1. Nu is the Poisson's ratio from section 2D table PRD. These values form the basis for all stress checks. The stress limits are straightforward and defined as follows. General primary membrane stress Pm must be less than or equal to allowable stress S. Local primary membrane stress PL must be less than or equal to 1.5 S. The combination PL plus PB must also be less than or equal to 1.5 S. These criteria ensure that the vessel remains safe against plastic collapse when analyzed elastically. To perform evaluation, we developed a 2D axisymmetric model. The 2D model is sufficient for this axisymmetric geometry and saves a lot of computation time while accurately representing the pressure, loading, and boundary condition. Here the internal pressure of 420 psig is applied inside the vessel. A thrust force is applied at the top surface considering both the area and internal pressure. This loading is the same as given in PTB3 example. Bottom face is only fixed in y direction. Rotation is fixed in z direction. This allows vessel to expand. Here you can see the stress classification lines or SCLs. 9 SCLs were defined, cutting through the wall thickness at critical points in the shell and head. These lines allow us to linearize stresses into membrane and bending components. Location include areas near the nozzle, the transition region, and the head crown. All areas where higher stresses are expected. Next, we validate the finite element model by comparing resultant force detection at the remote boundary condition. The value obtained from ASME, from FEA, and from a very basic hand calculation considering only the pressure load are in excellent agreement, which confirms that FEA setup is correct. I have created path lines in ANSYS. Along these path lines, stress linearization can be performed. There are 9 path lines defined, the same as in PTB3 example. Now if you look at the linearized equivalent stress along SCL1, you can see that the stress has been linearized across 49 points from outside surface to the inside surface. SEL1 passes through the flange weld region. In this plot, red curve shows the membrane stress, which remains constant at about 7040 psi across the thickness. Why 49 points? In ANSYS, when you define two endpoints for linearization, the software divides the path into multiple intermediate nodes, here 49. Point 1 corresponds to the outside surface. Point 49 corresponds to the inside surface, which is 0.375 inches thick. The bending stress starts around 9855 psi at the outside surface, which drops to 0 at the mid thickness, and then increases back to 9855 psi at the inside surface. The combination PM plus PB is obtained by combining the two. For example, membrane 7040 and bending 9855 is combined to get 13299 psi. Finally, the total equivalent stress, which includes membrane plus bending and peak stresses, reaches about 20,606 psi at the inside surface. Some of you may notice that adding 7040 membrane and 9855 bending directly gives you about 16,000 psi, not 13,000 psi. That's because the sum is not a scalar but a tensor based. When combining stresses, negative components may cancel out other. The equivalent stress is calculated from the combined stress tensor, not simple addition. If this seems unclear, let me know in the comments. I will make a separate video on stress linearization in detail. In ANSYS, if you click on a specific path, you can open a worksheet that shows the details. It shows membrane stress, bending stress, equivalent stress at the inside, center, and outside region. For SCL1, for example, the membrane equivalent stress is 7040, the bending stress is 9855, and the total inside equivalent stress is 20,606 psi, which matches with the table and the plot. Now let's look at the allowable stress values for material used. Allowable stress are given for both SA516 grade 70N and SA105. Multiplying by 1.5 gives the limit for PL and PL plus B. It is important to note, according to the code, bending stress are only calculated for local hoop and meridional components. Bending stress are not determined for stress parallel to the SCL or in-plane shear components. This ensures the evaluation is consistent with the code assumption. In this slide, the ASME result and FEA results are compared. The linearized equivalent stresses for all 9 SCLs are in very good agreement. Any small difference are due to the fact that PTB3 does not provide a CAD geometry. We must create our own model based on given dimensions, which can lead to slight variations. The important conclusion is that the limit criteria are satisfied for all 9 SCLs. You can also compare the equivalent von Mises stress plot with PTB3 figure 5.2.19 and linearized stress with PTB3 table 5.2.1.1. This completes the demonstration of elastic stress analysis using ASME approach, validating it with PTB3 example. Now we will move to the second example, which is limit load analysis. Example 5.2.2 limit load analysis. Our second example is PTB-3, example 5.2.2. Here we evaluate the same region of the vessel using the limit load analysis method as per clause 5.2.3. The objective is to check whether the computed limit load is greater than the factor design load. The factor load is 1.5 times the applied pressure, which is 630 psi. The same materials are used here as in the previous example. Why use 1.5 P? Why 1.5 times the design pressure? This higher multiply accounts for strain hardening and stress redistribution in real world condition. The 1.5 factor was derived through comparison with experimental burst data, making it a conservative margin of safety. It confirms that vessel can withstand 150% of the design pressure without reaching global plastic collapse. Reference is table 5.4 of ASME Section VIII Div 2. A load of 1.5 or 630 psig is applied. The thrust force is adjusted accordingly. In limit load analysis, the material is modeled as elastic, perfectly plastic, linear elastic up to the yield, perfectly plastic beyond yield. In FEA, the tangent modulus should ideally be 0, but we assign a very small value here 1000 to maintain numerical stability. The model from the elastic case is reused with new material definition. The load was increased step by step until 630 psi. At this load, the structure carried the pressure without collapse. The von Mises stress plot shows plastic region forming, but vessel remain stable. Thus the vessel passes the limit load analysis check. You can compare these plots with PTB3 figure 5.2.2.3 and 2 for validation. Now for the final example, we will discuss the elastic plastic analysis method. Example 5.2.3. Our third example is PTB3 example 5.2.3, which uses the elastic plastic analysis method as per clause 5.2.4. The objective is to evaluate the pressure vessel and check compliance with the code's rules for plastic collapse. This is the most advanced and most accurate method because it uses the full true stress and strain curves for the materials. Material property same as before. In this model, we include the full nonlinear stress strain curve, large deflection effects on, and kinematic hardening effects are also on. Only the true plastic strain versus true stress curve is passed into ANSYS as a multilinear data. In elastic plastic analysis, the load factor is increased further to 2.4 times the design pressure. This requirement comes from table 5.5 of the code and provide very strong safety margin. For this problem, the component must safely withstand 1008 psi compared to the design pressure of 420 psi. This ensures the vessel remain structurally sound even under significant overload. A load of 1000 psi is applied with thrust force adjusted accordingly. The von Mises stress plot shows high stress near the junction, while plastic strain plot confirms redistribution of strain. The pressure displacement curve remains stable up to 2.4 1000 psig. This plot is for a pressure load of 1680 psig to match with PTB example. However, the main objective is to show the plot is stable at 1008 psig. Here nozzle vertical displacement correspond to the top forging and shell radial displacement correspond to the maximum radial expansion for the shell. Comparison with PTB3 example 5.2.3.2 and 5.2.3.3 shows excellent agreement. To summarize three methods, elastic stress analysis showed the stress were with allowable limits. Limit load analysis confirmed the vessel could sustain 1.5 times the design pressure. Elastic plastic analysis confirmed stability up to 2.4 times the design pressure. All three methods demonstrate that the top head and shell region of the vessel is adequately protected against plastic collapse. This exercise shows how theoretical code rules translate into practical FEA procedures. By solving PT3 examples, we validate our methods and again gain a deeper understanding of real structural behavior. In future videos, we will move on to the other design by analysis failure modes in part 5 of Div 2, such as local failures, buckling, cyclic loading, and creep. For each of these, we will again solve PTB3 example step by step. This way, we'll not only learn the DBA methodology, but also see exactly how to use it in real engineering application. As always, please remember these examples are presented here for educational purpose only. For actual design and compliance, you must refer to the official ASME boiler and pressure vessel code and PTB3 documentation. If you found this video useful, please like, share and subscribe so you don't miss the upcoming lectures. A lot more clear, practical knowledge packed content is on the way. Thank you.